Okay, thanks for being here. Today I want to talk about bidirectional charging, about the protocols, the challenges, and the strategies we do in EVerest. My name is Andreas. I'm working at Pionics on EVerest. As I said, we will start what bidirectional charging is and why we should do it. Then some different charging and discharging strategies. And then we will have a look at the entire impact chain of it. And then I will give you some insights in EVerest, how we do energy management there. And then we will come to a conclusion. So what is bidirectional charging? I guess you all know what charging is. And I guess you all know what discharging is. And if you put both together, you have bidirectional charging. So with this, why should we do it? There are different reasons for it. At first, there was the climate change. This is why we have renewable energies with small producers and a decentralized production. And this is why we need grid stabilization. And for this, we can use electrical vehicles. And some personal motivations could be the price optimization during the charging. And you could also use your EV as emergency power supply, or just use the EV as a big power bank, for example, at the camping ground. Then we will start with a very first charging strategy, the fast charging. For this, we need an electric vehicle with a certain minimal and maximal charging power and specific battery size. And the goal is to charge this EV as fast as possible. And strategy is, okay, we just take as much as possible available power to charge the car. And in this scenario, we have an external restriction of charging power after 30 minutes. So you can see the result here. The green line, the charging power, which starts with 50 kilowatts and then drops after 30 minutes to 20 kilowatts because of this external limit. And after 2.5 hours, the EV is full and the charging session ends. So quite easy, straightforward strategy. A more complex one is the optimization of the PV produced energy consumption, and also with some other consumers in the local grid. For this, we need a photovoltaic system which has a certain peak power and daily energy yield. And a curve, so the most energy production will be around 12 a.m. And again, we have a scenario. The arrival time is at 11 o'clock. We have a state of charge of 10 kilowatt hours and a max charging power of 20 kilowatts in this scenario. Goal is to use as much of the PV produced energy as possible, and strategy is that we calculate the leftover at the grid connection point, so we have the PV production, subtract the other consumers, and with this leftover power we can charge. And if this leftover power is negative, we can discharge this leftover power to come to zero at the leftover energy. So here the result again. In the upper left you see the PV production in purple, in yellow some random other consumers. In the bottom left you see the leftover energy, and you can see until 11 a.m. We have some import of energy in the beginning and then some export of energy, and at 11 a.m. it drops to zero, and this is because, which you can see in the upper right, the charging power starts at 11 a.m. The EV arrives and starts to charge and brings this leftover energy to zero. And at a certain time, around 5 p.m., the EV starts even to discharge because the consumption is higher than the production, and we want to use the one's PV generated energy here. There's also the energy market, and we could do some price optimization, but no time to explain a strategy here. But in general, we can support the grid. The grid can use the EV, and For this, we would give some restrictions, a minimal and maximal state of charge, and then the grid can decide when does it make sense to charge or discharge the EV. Now I want to have a look at the entire impact chain of bidirectional charging. I took this diagram from a research project we are part of. It's quite big. I made an easier version for you, but it's important to have in mind there are a lot of players in this system that are part of this. And first, we have a look at this section, so the communication between the EV and EVSE, which is done by ISO 15118. We already heard about it today. So it defines the procedure of the charging session, and it provides then tooling for smart charging and also bidirectional charging. Here we have a quick overview about the features in the different versions of ISO 15118, and you can see the -20 version brings the features we need for bidirectional charging, so smart charging and pause and resume features. Then we have another area, the communication between the EVSE and the OCPP backend. So for this, we use OCPP to communicate. And there again, we have different versions, and the newest one, the 2.1, brings features for smart charging and the support for bidirectional charging. So also some necessary stuff here. Then here we have the local consumers and producers of energy. They can talk with each other via EEBUS, for example, and EEBUS also enables the interaction with the grid and defines also the behavior of these devices in specific use cases. And now I want to dive more into EVerest and show you some internals. Again, some system architecture. This one is inside of EVerest. So the rectangles are our internal modules. The ovals are some external service, and the color purple means that this area is work in progress. I want to break it down for you. On the left, we see the communication to the EV. So here, ISO 15118 is important. We have the EVC manager, we have the ISO module, we have the hardware driver, in this case, the Yeti driver, and the EV. On the right side, we have OCPP, which also does some authorization. This is not important right now for us, but it connects the EVC manager to the OCPP backend. In the bottom right, we can see the EEBUS related stuff. This is connected to the energy manager and will give some limits to charge and discharge. The energy manager, how does it work? So even one layer down, it has a representation of the energy tree in it. So we have, in this case, two EVSEs, two connectors at one charging station. They each have a circuit breaker, and they share also a circuit breaker with 63 amps in this case. And if one of these nodes wants to produce or consume more or less energy, it needs to make a request, and this request is brought up to the energy manager, so following the green arrows, and then the energy manager does some logic and brings back down to the node and responds with the distribution of the power consumption. Here we can see the energy tree in this architecture. So in the bottom right, the energy manager. Then there's some limit controlled by EEBUS, then some limit controlled by OCPP, and this what is left over can be used in the EVC manager. So now we come to the conclusion. What are today's problems? The most EVs and EVSEs don't speak ISO 15118-20. To address this issue, the one thing we do is testing the EVs in the field. And we have a nice repository with all the log files and with a nice table where you can have a look which EV has which features. Then another problem is, okay, an open standard doesn't mean automatically that we have an open implementation. This is why EVerest targets exactly this and implements this protocols and standards or integrate existing ones. And yeah, in some cases like EEBUS, which comes with a lot of overhead, it's quite hard to just do a simple implementation by yourself. So we are already on the positive side, on the outlook side. We have open software, as I mentioned, EVerest, which brings implementation for the ISO 15118 stuff and for the OCPP stuff for all the different versions. So on a good way there. And we have also some other open source projects. We already heard 3 of them today. We have, for example, for EEBUS, we have a EEBUS Go library, which we currently integrate in EVerest. We have CitronOS on the OCPP backend side, Steve and Maeve. And we also need hardware to run this open software on. And there is already hardware that can do this. There are more than 10,000 chargers in the field currently that already run EVerest. Then we have, for example, the FireSo board, which is built in a very modular way. And I also bring a configuration of it. It is here an AC configuration, but the board is also designed to do DC and bidirectional charging. And it can run EVerest. So it is already available. Then we have the YAC board as reference hardware. It is open hardware. It is already available, designed for AC and DC. It runs EVerest. Then we have the Yeti board. I brought also one, which is more designed to do AC, but it is also possible to do some DC stuff there. Also open hardware and also already available. So there we are on a good way on software and hardware. We're looking to the future. And last thing to say is get involved. There are multiple open source projects you could contribute to. In our case, in EVerest, we have open working group calls where you can just join, ask questions, bring in your ideas, and start contributing. And since there's no much time left, we can do a Q&A session in the hallway. Thanks.
Andreas, will you take care to repeat the question for the audience?
Yeah. We have 2 minutes to do Q&A here.
You talked about EEBUS as the way to talk to the building management system, but that's not your spec, right? That's somebody else's protocol. For example, Victron don't do that, but they do MQTT, and then there's a whole load of stuff.
Yeah.
I'm not aware of anything that was EEBUS. I've never heard of it before today.
So EEBUS is one way to do it. So you mean this slide, right? So EEBUS is one way, and something we are currently on it because it's so in Germany it's maybe more spreaded to use EEBUS, but it's also EEBUS is a bit of clunky and it's hard to say if it's the best choice to do EEBUS, but we will see what the future brings.
Is there also a strategy to prevent straining the battery of the EV, or is that just up to the BMS of the car itself?
Sorry, to do what with the battery?
Prevent straining of the battery, just overuse and decharging it. Or
I don't exactly.
care about it.
So you don't kill the battery by discharging and recharging it all the time.
Do you want to prevent it to discharge it too fast, or do you just keep the problem at the car?
The ISO 15118-20 protocol will care about correct charging and discharging, but of course you will have some usage of the battery, and the battery will getting worse with the time, as the same if you would charge and discharge while driving. But yeah, this. Yeah.
I think
Not
the
sure.
evidence is that it doesn't really hurt much.
Yeah, it doesn't take.
And there was recently a Tesla in America that's done it for 666,000 miles on the same battery.
Yeah.
And it's still running very well.
Yeah.
I think it's more temperature dependent when you're charging and discharging the actual current of the environment.
Yeah. So thank you for attending. Time is up.